Welcome to this explainer. Have you ever looked at a perfectly formed gemstone, or maybe just caught a snowflake on your sleeve and wondered, why? Why do they have such precise, sharp, geometric angles? Well, today, our main focus is Theme 1, Crystal Structure and Symmetry. We are going to dive straight into the fundamental laws of chemistry and physics to unpack exactly why solid matter behaves this way. We'll explore the hidden mathematical blueprints of nature, and eventually, we're literally going to travel deep into interstellar space to see what happens when these rigid laws completely break down.
But let's start with a really fascinating historical observation. Picture this. You take a hammer to a beautiful, flawless piece of calcite. That's essentially what René Just Hayu did back in the late 18th century. And just through the simple act of observing how those crystals cleave and shatter, he made this profound deduction. He said, in breaking a crystal into smaller and smaller pieces, one can arrive at polyhedral elementary bricks. I love that, because it perfectly captures our human quest to find order in nature. We've just always intuitively known that if you keep zooming in, you've got to eventually find the fundamental repeating building blocks of matter.
So, here is our roadmap for today. We are going to cover 1. The hidden order of crystals. 2. Elementary bricks. 3. Sphere packing. 4. Interstitial sites. 5. Symmetry and complex structures. And finally, number 6. Order versus chaos. Let's get right into it.
Section 1. The hidden order of crystals.
Our journey begins centuries ago. And keep in mind, this was long before we had fancy X-ray diffraction or electron microscopes. Natural philosophers had to rely purely on careful observation of the macroscopic world. It's an incredible story of deduction, honestly. Look at this timeline. In 1669, a guy named Nicholas Steno studied quartz crystals from entirely different geographic locations. He noticed that even though the overall sizes varied wildly, the angles between corresponding faces were always, mathematically, identical. This became the law of constant angles. Then, fast forward to 1748, Lomonosov took it a step further. He proposed that these structures were actually made of tiny, packed, spherical corpuscles. And finally, by 1822, Hayu formalized the whole thing into a theory of structural systems using those elementary polyhedral bricks we just talked about.
Moving right along to Section 2, Elementary bricks.
Okay, so what's really interesting here is how we mathematically define those microscopic building blocks that Hayu was theorizing about. We need a way to translate physical, tangible atoms into a universal language of geometry. And it turns out, a physical crystal is simply a mathematical lattice paired with a specific motif. That's the equation. A lattice is just a periodic, repeating array of abstract points in space. It's totally imaginary. It has no physical substance. The motif, on the other hand, is the real stuff, the actual group of atoms. It could be a single copper atom or a massive, complex molecule. When you attach that physical motif to every single abstract point in the lattice, boom, you get a crystal.
It's almost like a recipe. Let's see how this builds our crystal mathematically, step by step, from a single point into a full 3D structure. Step 1, we just pick an origin node. It's an arbitrary starting point. Step 2, we apply translation vectors in 3 dimensions. In crystallography, we call these vectors A, B, and C. By multiplying these vectors by whole numbers, we map out every single node in our 3-dimensional grid, creating what we call a unit cell, which is literally the smallest repeating volume of the entire crystal. And then step 3, we just add our atomic motif to each of those generated nodes. It's elegant, it's precise, and it scales infinitely.
All right, Section 3, Sphere packing.
So we know the math, but how do these atoms actually sit next to each other in real life? To visualize this, just imagine hard spheres. It's exactly like stacking oranges at a grocery store. If you want to fit as many oranges as possible into a display box, well, there's a right way and a wrong way to do it. If you just balance one layer of spheres directly on top of the layer below it, what we call the AA sequence, you get a simple cubic structure. It's non-compact. It leaves a ton of empty, wasted space. But if you offset the layers, kind of dropping the next layer of spheres right into the little dips or crevices of the layer below, you get a compact arrangement. Alternate 2 layers back and forth, the AB-AB sequence, and you get a hexagonal compact structure. Cycle through 3 offset layers, the ABC-ABC sequence, and you've got a face-centered cubic structure. These compact, tight structures are exactly how elements, like metals, naturally maximize their density. Which brings us to Section 4, Interstitial sites.
Here's the absolute secret to solid-state chemistry. Even in those tightest, most compact packing configurations we just looked at, empty spaces remain. You literally can't pack spheres without leaving gaps. These gaps are called interstitial sites, and they are incredibly vital for chemical reactions and for mixing different elements together. Notice the geometric difference here. You have a smaller tetrahedral site, which is wedged between 4 atoms, and a larger octahedral site surrounded by 6 atoms. When you pack spheres together, these two specific types of voids are just naturally created between the layers. And why does this matter? Well, when a solid interacts with smaller atoms, say when you're forming a crystal from 2 totally different elements like sodium and chlorine, the smaller ions will literally slot right into these specific tetrahedral or octahedral voids. The entire architecture of the materials around us depends on the size and shape of these empty spaces.
Section 5. Symmetry and complex structures.
Okay, let's step it up a notch. What happens when we mix different types of atoms in way more complex arrangements? Because this isn't just theoretical geometry anymore. This is the basis for advanced materials, like the superconductors that literally power our modern technology. Now, crystallography can feel a bit abstract, but this math directly applies to real-world stuff like perovskites, which have the general formula AbO3. Basically, in these structures you have a large cation, a smaller transition metal cation, and some oxygen atoms. The founder of crystal chemistry, a guy named Victor Goldschmidt, introduced this brilliant concept called the tolerance factor, represented by the letter T. This equation relies entirely on the precise ionic radii, the physical sizes of the atoms involved. It basically evaluates whether the sizes of these totally different atoms are actually compatible enough to form a stable, perfect cubic structure.
And this right here perfectly illustrates how slight, tiny mathematical variations in that tolerance factor lead to massive macroscopic changes in the whole crystal shape. If the ratio T is right between 0.95 and 1, the atoms fit together beautifully, and you get a perfect cubic structure. But watch what happens when the atoms are slightly mismatched. If T drops just below 0.95, the structure actually stretches into a tetragonal distortion. Drop a bit further, it shifts to orthorhombic. Go above 1, and the whole thing contorts into a hexagonal distortion. The sheer physical size of the atoms forces the entire macroscopic crystal to warp and change its fundamental symmetry. It's a literal dance between geometry and physics.
And finally, Section 6. Order versus chaos.
So we've spent this entire explainer marveling at perfection, right? The repeating lattices, the constant angles, the perfectly predictable geometries. But now, we are going to leave Earth. We're going to look at materials forming in the harsh, freezing environment of deep space. Because we have to ask a critical question that totally subverts everything we've just learned about the rigid laws of solid matter. What happens when the perfect symmetry disappears? What happens when matter is robbed of the energy and the cozy conditions it needs to organize itself into those beautiful High-U elementary bricks?
Well, out in space, inside these vast interstellar dark clouds, water ice forms amorphously. Because of the extreme cold and the incredibly rapid condensation, the water molecules just don't have the time or the energy to align into the beautiful periodic symmetry of a crystal lattice. Instead, they freeze instantly into what's known as amorphous solid water, or ASW. This material is highly porous and completely lacks long-range order. It is literally just a chaotic jumble of molecules frozen in place.
So if we don't have a regular lattice and we don't have a unit cell, how on earth do scientists even measure or describe this stuff? Instead of a neat little grid, astrophysicists and chemists have to use a statistical tool called a pair correlation function, often written as G of R. Because the distances between neighboring atoms aren't uniform anymore, this function measures the probability of finding an atom at a particular distance from another atom. Think of it like a mathematical fingerprint of the local, short-range order that's hiding deep within the macro-level chaos.
And the consequences of this chaotic structure, they are enormous for how atoms move or diffuse across the surface. In a perfect crystal, an atom moves smoothly. It acts almost like a temporary quantum mechanical wave packet, just surfing along. But in amorphous ice, the rules change completely. Because the potential energy wells are totally random and jagged, an atom quickly gets trapped or localized in a deep energy well. To move, it can't just flow smoothly anymore. It has to rely on thermal hopping. It literally sits there waiting for enough heat energy to physically jump out and into the next site.
I am going to leave you with this final kind of provocative thought. In those dark interstellar clouds, complex organic molecules, literally the very building blocks of life, are formed through chemical reactions on the surfaces of these chaotic, amorphous ice grains. The trapping of atoms in those random, jagged interstitial sites is exactly what allows them to meet and react in the first place.
So, if the chemical precursors of life rely on the chaotic, amorphous ice of space, is our human obsession with perfect crystal symmetry just an earthly illusion? Perhaps the true engine of creation isn't the perfect crystal after all, but the beautiful chaos of the amorphous void. Thank you for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.